Okay, for this problem, I want to suppose that I have a very thin wire. So thin that I'm going to treat its thickness as negligible, so I'm going to treat it as a one-dimensional object. And let's suppose that I've molded that wire into a shape like so. I'm going to introduce my axes, okay? So that it's the top half of the unit circle, and then this line along the bottom, okay? So this would be the point 1, 0, and this is the point -1, 0, okay? And the wire is not just the semicircle, but also that line along the bottom, okay? And let's suppose that my density function is y plus 1. And here the density would be giving me mass per unit length. So when we have a three-dimensional object, it's mass per unit volume. When we have a two-dimensional lamina, density would be mass per unit of area. If I've got a one-dimensional object, and I'm treating this thin wire as if it's one-dimensional, then the density function is mass per unit length. Okay. So if I say that C is the boundary around of this wire, and I integrate the density function ds, that should give me the mass of this wire. So that's one application. But I'm hoping that you've noticed that we have a slight problem with our curve C, and that's that it's not smooth. This part is smooth, this part is smooth, but I've got these sudden changes at these 2 points right here. So it comes in 2 different pieces, each of which is smooth. So we say that C is piecewise smooth. So I can say C1, that's going to be this line segment here, that's the bottom part of the wire. And C2, that's going to be this semicircle here. And we can actually say that C is C1 plus C2, and it's a piecewise smooth curve. And we do actually write it that way, that we write that we're just adding those curves together. So if I wanted to go around C, I would do what C1 tells me to do, and then C2. I'm choosing to illustrate this as if I'm going around counterclockwise. Turns out, and we'll address this directly later on, when I'm doing a line integral like this, the orientation of the curve does not matter. Okay. We will take a look at that later on, but I'm just going to state that now. Okay. So if I wanted to do the integral along C, I'm really doing the integral along C1 plus C2 of the density function. And I just break that up, of course, into 2 integrals. So the fact that we can work with piecewise smooth curves is really helpful, because often we're going to have the boundary of some region, and it does consist of multiple parts. Here we've got a semicircle and a line segment. If I had a rectangular box that has a left boundary, a right boundary, a top, and a bottom, but it's got those sharp corners where those sides meet. But we can work with that as a piecewise smooth curve. Does not matter how many pieces we have. Okay, so I'm going to need to just parameterize both of these curves. So if I look at C1, I'm going to say that's R1 of t, which would just be, looks like t0, y is always 0, and t would be varying from -1 to 1. Then R1 prime of t would be 1, 0, and that's awfully nice because the magnitude of R1 prime of t then is just constant at 1. I kind of like that. Okay. Now, if I look at curve 2, I think I'm going to just bump up here for that. Curve 2, I'll parameterize as R2 of t. And that I can just do with cosine t sine t. And that's going to have t varying between 0 and pi. Then R2 prime of t is negative sine t cosine of t. The magnitude of R2 prime of t is the square root of sine squared t plus cosine squared t but that's just 1. So these are some really nice curves because the scaling factor that I'm going to get in switching from integrating with respect to arc length to integrating with respect to t is just going to be 1. Gotta love it. Okay, so we basically are doing the integral along C1 of y plus 1 ds plus the integral along C2 of y plus 1 ds. And now let's switch both of those over to t. So for curve 1, we said t was varying from -1 to 1. Y plus 1, let's see, on curve C1, the y value was 0, so that just becomes 0 plus 1, which is going to be 1. Anytime I'm switching from ds to dt, I get a scaling factor, which is the magnitude of the derivative. In this case, that's just 1. I'm still going to write that down because I don't want to forget. So even if it does end up just being 1, which won't happen all the time, but does happen in this case, I'm going to choose to write that every single time. Okay. Plus, now for C2, that was this curve up here. T was varying from 0 to pi. Y was sine of t, so this becomes sine of t plus 1. Scaling factor dt, and my scaling factor again was the magnitude of the derivative. Once again, it ends up being super, super nice, and we just get 1. Again, I'm going to encourage you, even when that does happen, to write it in so that you don't forget that important step. All right, so here I'm just integrating 1. So I'm going to get 1 times the length of this interval, and the length of that interval is just 2. Plus, here, an antiderivative of sine will be negative cosine of t, and then plus t, and that's evaluated between pi and 0. So that's going to be 2 plus. Cosine of pi is -1. The opposite of that is going to be 1 plus pi. Minus, when I plug in 0, cosine of 0 is 1. The opposite of that is -1 plus 0. So, if I work that out, let's see, that's going to be 2 plus 1 plus pi plus another 1, so we get 4 plus pi would be the mass of this wire.